Topic is primary and secondary constants. So in the previous class, in the previous video, I have said what is an transmission line, why we are needing the transmission line. So that means in the field of electronics, it is very needed to guide the electrical energy from one point to another point. For that, we need a media, guided medium, that is going to be calling as transmission line. Okay, so whenever we are having the an electrical energy, that is nothing but an RF signals from the transmitter to the antenna. To move that, we need a transmission line and with a least power loss. So the loss of power will be depends upon the physical and electrical characteristics of our transmission line. That means whenever we require a transmission of RF signals from the transmitter to the antenna, we require transmission line with a least power loss is going to be done. And whenever we are calling as a least power loss, that will be depends upon the physical and electrical characteristics of our transmission line. So what are the physical characteristics means? That is nothing but an area and length, cross section area, and number of conductors which are going to be used. Okay, so like that comes under the physical characteristics. And whenever we are having the electrical characteristics, which comes under the resistance, inductance, capacitance, conductance, all of this. Okay, so comes under this. These transmission lines are having a traditional transmission lines. That means normally the traditional transmission lines are not going to use at high microwave frequency ranges. These can be not used means a special type is going to be introduced for the guided medium at microwave frequency ranges, that is going to be calling as waveguide. So these waveguides are used to transmit the microwave signals from one point to the another point with a less power loss. So like this it can be done with this. Okay, so this is about the transmission line. So when we are coming for the types of transmission lines, we are having number of types, and basically it is having the parallel transmission line, twisted pair transmission line, coaxial cable, waveguides, fiber optic cables. Like this we are having number of types under this. And when we are having the wireless, it is having an wireless communication purpose, we are having unguided media. That is we can say we are using as air as a media. Okay, so like that we are having number of transmission lines. And when we are having the transmission lines, in the previous video I have said what is the parallel wire type, what are the drawbacks of parallel wire type, and what is the twisted pair type, and what are the drawbacks which are going to be coming with the coaxial cable, and what are the drawbacks of coaxial cable, and why we are going to be use the waveguides, and why we are using the fiber optic cables. Like this we are having number of things in the previous session. Okay, so we have explained each of the cable which comes under this. And I want to repeat that waveguide transmission media. Why? Because I have said that this chapter is going to be in the ranges of microwave frequency communications, that are microwave communication. So I would like to have this repetition of this guided media. That means the waveguides are going to be used very frequently for our microwave frequency ranges. So what is the use of microwave waveguide means? It is having an hollow metallic tube for transferring of electromagnetic energy, and it is having what is the specialty means? Internally the cross section is going to be uniformly distributed along the waveguide. That means at all of the positions the waveguide is having the same area of cross section. Okay, so that is a specialty of waveguides. And under the waveguides we are having based on the shape, it is divisioned as a rectangular waveguide, circular waveguide, elliptical. Okay, so based on the shape it is going to be classified. These are most frequent than the transmission lines. There are two-wire transmission lines than the coaxial cables also. Why? Because it is having the low radiation losses in this. Okay, so that's why we are going to be using the waveguides than the other transmission lines. Okay, so this is about our waveguides. So in this session, what does the main objective means? That is equivalent circuit of a transmission line, primary constant of a transmission line, and secondary constant of a transmission line. So what are going to be calling as primary and a secondary constant of a transmission line? So basically the parameters of transmission line, that means whatever where comes under the transmission lines, that parameters are going to be division into two parts, calling as primary constant and secondary constant. So it is nothing but an basically parameters, that means based on the parameters of transmission lines, it is division into primary constants and secondary constants. So for having the equivalent circuit of a transmission line, we have to know about the conductors which are present in a two wire lines. Okay, in that the dielectrics are also present between them. So it is also clear that the conductors can be having of any length. Okay, so the conductors also have the same diameter also. Okay, if both length and diameter are associated with the conductor, then resistance and inductance must be present there. Okay, so why we are saying this means, if we having a transmission line, in that we are going to be calling as conductors are present in the two wire line. Okay, so whenever the two wire line consisting in that, we have an dielectric as a air. Okay, that is going to be present between them. Okay, so the conductors may be of any length, it can be having any length. Okay, so if we having any length, the conductor is also having some diameter also. So when both length and diameter is going to be taken with the help of diameter, that is with the consideration of conductor, then in that the resistance and inductance must be present there. So if wires are going to be separated from each other by placing the dielectric between them, then the leakage of charge will take place. Because of the dielectric that we are using in an insulator material, which can be a perfect insulator. That means we can having the resistance, we can having the inductance, and at the same time it is also acting as an insulator. Okay, so when we are having this perfection of the equivalent circuit, we can have this diagram. Okay, whenever we are using the transmission line, that is two wire transmission line, in that we consisting of inductance, that is flux is going to be generated while we are transmitting some voltage across that. While we are having some voltage, it is having some inductance, that means the flux is going to be generated, which will be act as an inductor. Okay, so any material which consisting of a resistance, that's why it is going to be calling as resistance. And whenever we are using the two wire system, in that it is nothing but a space is going to be there in between the two wires, and which will be acting as a capacitor, parallel plate capacitor. So whenever we are having the R, the G is also having in this, the G is nothing but conductance. Okay, so like this, the equivalent circuit of a transmission line, which consisting of all of the parameters which is seen in the figure. Okay, so like this, it is having number of parameters, that is L, R, C, G. Okay, L is nothing but an inductance, and R is nothing but an resistance, and C is nothing but an capacitance, and G is nothing but an conductance. So like this, we are having all of the components within the transmission line. Okay, so this is about the equivalent circuit of a transmission line. So when we are having the equivalent circuit of a transmission line, all the quantities, that is resistance, capacitance, and shunt conductance, are calculated with respect to the length of conductor. That means resistance, either we have to know about the resistance, means that will be depends upon the length of our conductor. Okay, so all of the quantities that are resistance, capacitance, and shunt conductance are calculated with respect to the length of the conductor. The inductive resistance has a greater value than that of the resistance with respect to the radio frequencies. That means the inductive resistance is going to be very much higher than that of the resistance with respect to the radio frequencies. So the value of capacitive susceptance is also much more than that of the shunt capacitance. Okay, so capacitive susceptance is also going to be very more than that of the shunt capacitance. So these all the quantities are working along the length of line. So if we ignore both R and G, then we can consider the circuit as lossless. Okay, so when we ignore this both R and G, then we can consider as the circuit as lossless line. Okay, so that is the main note, that when we are having some R and G, it is going to be ignored when the circuit is going to be lossless line. Okay, this is about the equivalent circuit of a transmission line. And this is also a circuit which comes under the L and C, that is equivalent circuit of a transmission line which consisting of L and C. How it looks means this is an figure. And the next one is primary constants of transmission line. The primary line constants are the parameters that describe the characteristics of conductive transmission lines, such as pairs of copper wires. Okay, so we can say that in terms of physical electrical properties of the line initially. That means I have said that we are having some physical properties and electrical properties. So like this, in the primary line constants are the parameters which will be describing the characteristics of conductive transmission lines, such as a copper wire pair. Okay, so in terms of physical electrical properties of the line, so the constants are, what are that constant means, when we are calling as in physical and electrical properties of the line, which will comes under the conductance, resistance, inductance and insulators. Okay, these will comes under the primary constants of our transmission line. So initially we can say with the symbols as R, L, C and G. So what is an R means? It is a resistance. What is L means? Inductance. C is nothing but an capacitance. G is nothing but an conductance. So these are primary constants which comes under the transmission line, and the constants are going to be differentiated or eliminated in terms of the unit length. Okay, that can be defined as in terms of per unit length. Okay, so that is the primary constants of transmission line. And what are the primary constant means? I have said that is resistance, inductance, capacitance and conductance. So the first one is resistance. It is defined as the loop resistance for unit length of line. It is defined as the loop resistance per unit length of line. It can also be said that it is the sum of resistance of both wires for unit line length. So the resistance is going to be calling as, it is defined as the loop resistance per unit length of line. It is the sum of resistance of both wires for unit line length. Okay, so it can be given as that unit is going to be ohms per kilometer. In this you have to note that I have written only K, that is nothing but an M is also present, that is it is units are ohms per kilometer, km. Okay, so that is the first primary constant of transmission line. And the next one is inductance, that is it is defined as the loop inductance per unit length of line, and it is also calling as, it is the sum of inductance of both wires for unit line length. Okay, so it is defined as, it is having some units given as henries per kilometer. I have said that any primary constant can be given per unit length of our transmission line. So like this, the inductance is also going to be the sum of inductance of both wires for unit line length, and it can be given as henries per kilometer. Okay, these are the units under the inductance. So these two are the primary constants of our transmission line. Not only with the two, we are having another terms, that is capacitance and conductance. So what is a capacitance means? It is defined as the shunt capacitance between the two wires per unit line length. The capacitance can be defined as shunt capacitance between the two wires per unit line length, and it is having some units. It is given as farad per kilometer. It is defined, the units are farad per kilometer. And the next one is conductance. So the what is conductance means? It is defined as shunt conductance between the two wires per unit line length. The conductance can be given as shunt conductance between the two wires per unit line length. It can be given as mhos per kilometer. That is, it is the opposite of resistance, the reciprocal of resistance, that can be having as conductance of transmission line. So initially, the primary constants of our transmission lines are resistance, inductance, and capacitance and conductance. These are the primary constants of our transmission line, and comes under the secondary constant. These are nothing but an electrical or physical characteristics of our transmission line. They are not going to be considered as an physical or electrical properties of our transmission line. Other than that, that can comes under the secondary constants of our transmission line. So under that, the first one is characteristics impedance. So what is the characteristic impedance means? It is the ratio of voltage and current on line. That is, it can be defined as the ratio of voltage to the current at the input of a infinite line. That means whenever we are having a transmission line, the beginning or ends are going to be calling as the starting points of our transmission line. At that, what is an voltage to the current at the input of that particular infinite line. So that can be given as characteristics impedance. Okay, so it is defined as, it is denoted as Z0. Okay, that comes under the characteristics impedance. So the characteristic impedance depends only on the line geometry and the dielectric material, and it is not a function of length. And it has units of ohms, but not the same as the resistance of the wire in the line. That means the units of the characteristic impedance is also going to be the ohms only, not with others, but it is not same as the resistance. Okay, so that is the main difference under the characteristic impedance. So whenever we are having the characteristic impedance, it is also defined as the impedance measured at the input terminals of the line when the line is infinite. So I have said that whenever we are having the long length of line, which is infinite line at the input side, that means the starting points which are there, at that we are going to be measuring the impedance, that is going to be calling as characteristic impedance. Okay, that is Z0, and this Z0 can be given as Vz by Iz. That is, I have said that it is the ratio of voltage to the current is going to be calling as characteristic impedance. Okay, and when we are having the characteristic impedance, so the characteristic impedance at a high frequency is going to be different, and at low frequency is going to be different. That means at radio frequencies are going to be different. Okay, so in order to calculate the characteristic impedance, first of all we have to know about the gamma Vz equals to minus R plus j omega L into Iz. So Iz equals to minus of G plus j omega C into Vz. Okay, so from this equation we are having any of one can be given, but when we are having some formula under the characteristic impedance, we have that is Z naught equals to V by I. That means from the V we can having the conclusion of Z naught also. So when we are having in this equation, that is Vz equals to this, instead of having the Iz, see, so see in this you can see this equation is going to be Vz equals to minus of R plus j omega L into Iz. So when we are having in this, in order to by our division with this, we are going to be getting as this, that is Vz equals to minus of this R plus j omega L into Iz by this one is going to given this like this. Okay, that means Vz by Iz, but you can see that we are getting as gamma also. Gamma by gamma is written 1, and in this the minus of minus means it is going to be cancelled, and it is similarly R plus j omega L into Iz by Vz. So you can see from this equation that Vz by Iz equals to R plus j omega L by G plus j omega C into Iz by Vz. Okay, so from this we can get as Vz by Iz equals to this one, that is R plus j omega L by G plus j omega C. Okay, so that is the equation for our characteristic impedance, where Z0 is the characteristic impedance and R is the conductor resistance in ohms per unit length, and L is the inductance in henries per unit length, and G is the dielectric conductance in mohms per unit length, and C is the capacitance in farads per unit length. So for an RF line, R and G are going to be 0. Okay, for radio frequency at high radio frequencies, the R and G are going to be equals to 0. That means you can get as j omega L by j omega C under root of j omega L by j omega C. The imaginary part, that is j omega is going to be cancelled. So we can have from this, that is root of L by C. Okay, so that means the characteristic impedance which will be depends upon the inductance and the capacitance of our transmission line. Okay, and the current and voltages are going to be in the same phase of our characteristic impedance. So that is the secondary constant of first part, and the next one is propagation constant. So the propagation constant is of a uniform transmission line per unit length is going to be defined as natural logarithm of the vector ratio of steady state voltages of currents or voltages entering and leaving the structure. So by this we can give as the P is going to be log E, that is natural logarithm value into I1 by I2. So I1 is the button currents, or we can say in terms of voltages or currents. So if we have the currents, that is given as I1 by I2. Okay, the currents which are entering and leaving the structure, and when we are having the in terms of voltages, that can be given as log E V1 by V2. It is also same, that is voltages entering into the structure and leaving into the structure. Okay, so like this we can say the propagation constant. So the propagation constant which will gives the way in which the voltage and currents varying with length along the transmission line. Okay, so that is the propagation constant. The propagation constant which will governs the way in which the voltage and currents vary with unit length along the transmission line. I have said in this. So whenever we are having the propagation constant, that is equal to the square root of the product of series impedance and shunt admittance. That can be also given as PE is equals to under root of Z into Y. Z is with a button Z is the impedance and the Y is the admittance. Okay, so whenever we are calling as an admittance, that is in the shunt, and whenever we are calling as a impedance, that is going to be in the series. So that's why the propagation constant, that is P, equals to under root Z into Y. Okay, where Z is equals to the R plus j omega and Y is equals to the G plus j omega C. So you can substitute its values under the P. Okay, that means the P is equals to under root of R plus j omega L into G plus j omega C. And instead of that we can also say as P equals to alpha plus j beta. Okay, the P can be given as alpha plus j beta. So what is alpha means? It is an attenuation constant and B is the phase constant. Okay, it is also given as this. And the next one is attenuation constant. The real part in the propagation constant, that is alpha, is calling as attenuation constant. That means whenever we are having the secondary constants of our transmission line, the first one is characteristic impedance and the second one is propagation constant, and to have the third property, that is attenuation and phase constant, in order to understand that, it is given from the second constant, that is propagation constant, as P. So where P is given as alpha plus j beta, and from that the alpha is going to be calling as attenuation constant, that is real part in our propagation constant is going to be calling as attenuation constant, and which will be determining the attenuation, that is reduction in the voltages and current along the line. That is the attenuation constant. And when we are having the attenuation constant, what are the units of attenuation constant means, which will be given as in Nepers per kilometer. Nepers per kilometer, that is the attenuation constant. And the next one is phase constant. I have said that the attenuation constant is the real part, and where phase constant is the imaginary part of our propagation constant. So it is going to be calling as phase constant. And the phase constant which will be determining the phase variation of our voltages and currents along the line. That means in the propagation constant only we are saying about the transmission line, that whether it is having some attenuation in voltages and currents along the line, or it will determine the phase variations of our voltages and currents along the line. And whenever we are having the phase constant, that can be given, that is the units are radians per kilometer. Radians per kilometer, that is the phase constant. And the next one is wavelength. Okay, so first of all, in order to have a wavelength, it is defined as the distance that a wave travels along the line per one cycle. The wavelength is defined as the distance that a wave travels along the line per one cycle, that is 2 pi radians. Okay, so in order to find out that wavelength, this is an abbreviation to have this, that is C equals to lambda f, that is wavelength into frequency. The C is the velocity of the light wave. Okay, and where C is having some value, that is 3.0 into 10 to the power of 8 milliseconds. Okay, and next lambda is the wavelength and f is the frequency, and speed of the light, that is c equals to f lambda, and the frequency is nothing but c by lambda, and the wavelength is going to be depends upon the speed of the light, that is velocity of the light wave and frequency of the wave. So that can be given as wavelength. So in this session I have said what is the equivalent circuit of a transmission line, and what are the primary constants of transmission line and the secondary constants of our transmission line. So let us have a quiz. Which of the following parameters is not a primary parameter? Which of the following parameter is not a primary parameter? So the first option is resistance, and the second option is attenuation constant, and the third option is capacitance, and the fourth option is conductance. So please note this question. So which of the following parameters is not a primary parameter? The first option is A, that is resistance, B, attenuation constant, C is capacitance, and D is conductance. So what is an correct answer? That is B, attenuation constant. Why? Because I have already said that the primary constants of our transmission line are resistance, inductance, capacitance and conductance. And when we are having the attenuation constant, the attenuation and the phase propagation constant are going to be calling as secondary parameters, that is secondary constants of our transmission line. So for that reasons you can pick up the odd one, that is nothing but an attenuation constant. That means which of the following parameter is not a primary parameter means it is nothing but a primary constant, which is not a primary constant. Resistance is a primary constant, capacitance is also primary constant, conductance is also going to be primary constant, but the attenuation constant is the odd one, calling as secondary constants of our transmission line. And next question. Which primary parameter is uniformly distributed along the length of the conductor? Which primary parameter is uniformly distributed along the length of the conductor? The first option is G, and the second option is C, and the third option is L, and the last option is R. Okay, so you can have an abbreviation of this also. Why? Because what is G means it is the conductance, that is reciprocal of R, and what is the C means it is resistance, and what is the L means it is inductance, and what is the R means it is resistance. So please note this question. Which primary parameter is uniformly distributed along the length of the conductor? So the first one is G, that is conductance, and second option is C, that is capacitance, and the third option is L, that is inductance, and the last option is R, that is resistance. So what is the correct answer? So that one is D. The resistance is a primary parameter, there is a primary constant that is uniformly distributed along the length of the conductor. It depends upon the cross section area and the length of the conductor. That means the D option, that is resistance, is going to be uniformly distributed along the length of conductor. Okay, so that is the correct answer. And the next question is, the primary parameter that is associated with the magnetic flux linkage is going to be, the option A is R, that is resistance, and option B is L as a inductance, and option C is conductance or capacitance, and the last option is G, that is conductance. Okay, so these the primary parameter that is associated with the magnetic flux leakage is going to be R, or L, or C, or G. So what is an correct answer? Please note this question. The primary parameter that is associated with the magnetic flux leakage is, the first option is R, that is resistance, and the second option is L, that is inductance, and the third option is C, that is capacitance, and the last option is G, calling as conductance. Okay, so what is an correct answer? And that is B. So the primary parameter that is associated with the magnetic flux leakage is going to be the B, that is inductance. So when the conductors carrying current, the conductors will be surrounded and linked by magnetic flux, and the flux linkages per ampere of current that will gives rise to the effect of inductance, and it is denoted as L. That means whenever we are having some current carrying conductor, so when we have some current across the conductor, the magnetic flux is going to be generated, and that flux is going to be generated along the rod or along the conductor. Okay, so that flux linkages per ampere of current which will gives rise to the effect of inductance, and it is denoted as L. Okay, so the primary parameter that is associated with the magnetic flux linkage is going to be the L. That is correct answer. So the next question is, find the characteristic impedance expression in terms of inductance and capacitance parameters. Find the characteristics impedance expression in terms of the inductance and capacitance parameters. So that means we are having characteristic impedance. Okay, so which is in terms of inductance and capacitance, so choose that correct answer. So the first one is Z0 equals to under root of LC, Z0 equals to LC, Z0 equals to under root L by C, and Z0 equals to L by C. So what is an correct answer? So please note this question. So find the characteristics impedance expression in terms of inductance and capacitance parameter. So what is an correct answer? That is C, that is Z naught equals to under root of L by C, that is inductance and capacitance. Under root of L, and L is nothing but an inductance and C is nothing but an capacitance. So the characteristic impedance is given as by the square root of ratio of inductance to the capacitance, that is going to be having in this expression. Okay, the third one is the correct answer. Next question. When a transmission line has the load impedance same as that of the characteristic impedance, then the line is said to be. When a transmission line has the load impedance same as that of the characteristic impedance, the line is said to be what? Okay, the first option is parallel, the second is perpendicular, and the third one is polarized, and the fourth one is matched. So what is an correct answer? Please note this question. So when a transmission line has load impedance same as that of the characteristic impedance, then the line is said to be either parallel or perpendicular or polarized or matched. So what is an correct answer? That is D, matched transmission line. Okay, so when a transmission line impedance is same as that of the characteristic impedance, then the line is said to be a matched line. In such cases, full transmission of power will be occurs with a minimum loss of power. There is a minimum loss is going to be there when we use the matched line. Okay, that means when the impedance, the load impedance is same as that of the characteristic impedance, then the line is said to be matched. So when it is going to be used, the full transmission of power, that means total power is going to be transmitted, and which is having some minimum loss of power. Okay, that can be occurred while we are using the matched line. So this is about this question. So in this session I have said so much of things. Okay, so that is primary constants of our transmission line and secondary constants of our transmission line. So I have explained each terms. Okay, what is a primary constant and what is a secondary constant, and we are also known about the equivalent circuit of our transmission line. So I have said that what is a transmission line and why it is going to be needed, and whenever we are having some parameters, we are having some performance characteristics, that is physical and electrical parameters, which will depends upon the transmission line choosing. Okay, so in this, whenever we are having a transmission line which will be acting as a two-wire transmission line. Okay, so whenever we use that two-wire transmission line, we will have the resistance, inductance, conductance and capacitance. So all of these four parameters can be present whenever we use the transmission line. Okay, so this is a best example of this. Okay, so that means in the transmission line we can calling as a two-wire transmission line. So in that we will present the L, R, G and C also. Okay, that means we can having the resistance, inductance, conductance, okay, and capacitance. So like this it is going to be affected, and when we are having the equivalent circuit, after that what are the primary constants means that are resistance, inductance, capacitance and conductance, and what are the secondary constant means characteristic impedance, that is Z0, and propagation constant, okay, that is P, and the next one is attenuation constant, and the last one is phase constant. These are nothing but we are calling as secondary constant, and along with that we are having the wavelength also. Wavelength comes under the secondary constant. Okay, this is about the primary constant and secondary constants and equivalent circuit of our transmission line. Okay, thank you.